I wonder if this one converges or diverges. And if it converges, does it converge absolutely or does it converge conditionally? And again, let's review that. An alternating series converges absolutely if it's alternating positive, negative, positive, negative, positive, negative, da 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 da. If this adds up to be some I almost fell over right there. Trip over myself talking about this stuff. If this adds up to be some specific number, it would converge with the alternating. But then if all the positives add up to be a specific number, and if they converge as well, then we say that we have absolute convergence. Meaning, whether this thing is alternating or just straight up positive, it's going to converge. That would be absolute convergence. And so in the process of doing this, we start by dealing with the alternating series first. Because if the alternating series doesn't converge, all bets are off, nothing. Whole thing diverges. Whether it's positive or negative, whole thing diverges. So that's where we start, and that's where we'll start this problem. So in this context, the toggle factor, the alternating factor, is -1 to the n, which means that our absolute valued explicit term would be 2 to the n. So we're going to use, bear with me now, the alternating series test on this, and if this converges, then we will be able to say, all right, good, we have convergence for the alternating series. Now we'll determine if the positive aspect only of the series would converge. That would be a separate issue. And then if that converges, we have absolute convergence. First things first, does this series converge? We'll test it with these two criteria. Criteria number 1, the limit as n approaches infinity of 2 to the n equals 0? No. Clearly not. This one diverges. Diverges. Alternating, diverges. Positive, it just diverges. From the very beginning, done. We know that it diverges. Let's move on to the next one. Okay. The next one's a little more complicated. We'll leave that on the board. And the next one says, here's your toggle factor, -1 to the n plus 1 multiplied by n over n squared plus 1. And I want to know if this one converges conditionally, so only that would converge. That would be conditional convergence. If it converges absolutely, which would mean that this converges as well as this one, or if it just diverges, which we just encountered in the previous problem where we were like, hey, that just from the very beginning diverged, whole thing diverges. All right, here goes. Let's first of all identify let's run into another chair here. Trip over myself, running into chairs. Man, I love this stuff. It's great. Start like writing on my face any minute now. I have n over n squared plus 1. There we go. That's what I have. The sun shining in right there on it, illuminating it. It's beautiful. This is the positive aspect of it. And we're going to test with the alternating series first. We'll do that. If we get beyond that, we will at least be able to say we have conditional convergence, and then we'll move on from there. So here we go. Because I'm going to need this space because I know where this is going, which implies that you know where it's going to. Let's just go ahead and do this right here in this brief little space. The limit as n approaches infinity of n over n squared plus 1. This is essentially the nth term test. This is equal to, well, 0. If this was a graph with a horizontal asymptote, the horizontal asymptote would be at y equals 0. So, mission accomplished. We have checked that one off for the alternating series test. We're good so far. Let's move on. Is any given term less than the one before it? And this is going to be a little bit trickier, but any given term is less than, the one I worded that well. So n plus 1 squared plus 1, is that less than or equal to n over n squared plus 1? And it looks a little bit tricky, so let's just continue to finagle this a little bit. But we're going to have n plus 1 over n squared plus 2n plus 1, so plus 2, less than or equal to n over n squared plus 1. And the more we look at this, the more, first of all, that doesn't factor. I'd love for it to, but it doesn't. The more we realize that this denominator is going to have a higher magnitude than this denominator consistently. This 2n is going to cause this to be enough bigger than this to be significant. What about the n plus 1 in the numerator? It's not going to be significant. And you can try it. If you wanted to grab a calculator, you could type this in as a function using x's, use this as a function, and then type 1, 2, 3, 4, 5 in the table, and you'll see which one is consistently bigger. Not always the best way to do it, but it's a good way to get an indication of what's going on. And I'll go ahead and tell you, just based on the structure of this thing, no matter what you try, you're always going to end up with something that is true. We have so far passed the alternating series test. That means this converges at least conditionally. Maybe, just maybe, it converges absolutely. So I'm just going to come up here to the top, and I'm going to be like, this converges, well, if I could spell C-O-N-V, converges. All right, converges. Okay, I'm leaving you hanging because there's something else. Does it converge conditionally? Does it converge absolutely? I don't know. We at least have conditional convergence because we just passed the alternating series test. All right. Now, let's try to pass just a regular old, any test I want to use kind of test. And I want to use the... Okay, first of all, it's not geometric. So we can't just use that. It would be fun. I wish we could, but we can't. So not geometric. Lots of other tests. Let's see. Ratio test is going to be very difficult to do algebraically. Ratio test is really good for things that involve factorials and exponentials. And this one looks a lot like it could be, blue marker, written like a function. Aha, fun stuff. Let's pretend for a second that this was the function, and it would be x over x squared plus 1. Is this, haha, integral test, you know it's coming, it's fun. If, I keep trying to convince you it's fun. If I had this function, would it consistently be positive? Yes. Would it, because I'm dealing with 0 and up. Would it be, well, if it was 0, then I would have 0, but beyond that it would work. So yeah, we're good. It's good. Would it be decreasing? Yes, because this denominator is going to level this thing off down kind of like a horizontal asymptote. So is it decreasing? Yes. Is it positive? With the exception of plugging in 0, yes. And really, it's okay that we would plug in a 0, get 0, which is technically not positive, because we can, if you wanted to, you could start this process somewhere else. We could start the process at 1 and then move on from there, which I think I'll do in the process of doing this. It's kind of neat that you can just be like, you know what, 0 breaks the rules, so we're just going to start it at 1. If we consistently would break the rules throughout, that's a problem, but we can pick a new starting point. Totally works. Trust me, I've done it before. And so positive, if we break the rules. Decreasing, yes. Continuous, yeah. No discontinuities on this. Totally fine. So let's move on. What we're going to do is the integral from 1 to infinity of x over x squared plus 1 dx. And we're going to just keep working with this. Well, you can't go to infinity, but you can pretend to with limits. So the limit as b approaches infinity from 1 to b of x over x squared plus 1 dx. And then we'll just keep going with this. All right, we're going to use some u substitution, and we're going to do it kind of in our head. So I'm not going to like turn it into u's and all that stuff. But if I said u was the denominator, then I would have 2x as my derivative. I don't want 2x, I want 1x. So I really would end up with 1/2. Whoops, forgot my limit. Hate it when that happens. Limit b approaches infinity of 1/2 natural log, because that's the denominator. By the way, it looks like arctan, but it's not, because of our numerator being x, not some constant. And the fact that this is x squared. Anyway, natural log of x squared plus 1. I'd love to put absolute value bars on that, but everything we're dealing with is positive anyway. Or 0 if we wanted to go backwards on that, but there we go. From 1 to b. Pause, double check your work, make sure you're good. Are we good? I feel great. Left some equal signs off, but I feel great so far. And we're moving on. Okay. Have the limit as b approaches infinity of 1/2 natural log of b squared plus 1. Tell them what is 1. You get some calculus. You get some calculus, and you get some calculus. 1 squared plus 1 is going to give me 2. Natural log of 2. And that's what I have. Okay, here goes. Pausing to make sure I'm right, and I'm right. And we'll move on again. Here's where my mind went, but it's kind of irrelevant. 1/2 could become an exponent, and I have 2 to the 1/2, which would be the square root of 2. So I could do that. Not necessary, though, because here's the deal. The limit as b approaches infinity. So I'd have the natural log of infinity squared plus 1. That's pretty big. So this diverges. Okay, because, all right, let's not lose track of the big idea. I want to know if this converges or diverges. I know it converges. I don't know if it's absolute or conditional unless I have done the alternating series test and then some other test, which in this case diverged, which means this. You don't have to write this down. If I generated these terms and added them for the rest of my life, that would converge. If I pretended like they were all positive, they would diverge. For that reason, this converges, but only if it's alternating, so it converges conditionally. And let's clean that spelling up, and that is it. Just kick the chair again. It's right there. That's how I feel about this problem. Yeah.